As Daniel already said, I'm Ben Leather and I'm in the final year of my PhD at University College Dublin. And what I'm here to present is a new alternative hyperboloidal method for frequency domain self-force calculations, and then implement this with a multi-domain spectral solver. So this was the subject of a recent release on the archive. You can find this preprint via the archive number shown or by scanning the QR code, which is on every slide. So let me briefly introduce you to this new approach. So for the uninitiated, hyperboloidal surfaces are space-like surfaces that behave like a space-time hyperboloid near null horizons. So unlike normal time coordinates, hyperboloidal coordinates foliate the future event horizon instead of intersecting at the bifurcation sphere, and they foliate future null infinity as opposed to intersecting at spatial infinity. So you can see this in the Carter-Penrose diagram on the right here. Thin red dashed lines depict the standard Schwarzschild exterior time surfaces, while the thick blue lines depict hyperboloidal time surfaces. So typically in perturbation theory, it was alluded to before by Sam and Ollie, we solve these perturbations along red, time, or t slices, and the majority of self-force calculations are carried out within the frequency domain, where computing this perturbation reduces to a set of ordinary differential equations. So in general, on t slicing, the frequency domain wave equations for the self-force problem have the following form here, shown for just a single scalar field for simplicity, where this delta is a second order differential operator, and the one can encounter three types of source, being distributional, wheel tube, or unbounded support. So distributional is the first case we consider. So this is a distributional source on the part with support on the particle's orbit. So this case arises when we directly solve for the retarded field with a point particle source, as is quite common in black hole perturbation theory. The second scenario we consider has extended sources with compact support around the particle, i.e. cases in which the source functions are often defined on a compact wheel tube between two radial points. So these types of sources occur in eccentric orbit or effective source calculations. And the final one, the relatively unknown one, is sources with unbounded support. And these arise in various recent self-force calculations. So the two timescale approach to second order calculations that Sam kind of touched on introduces these quantities called slow time derivatives of the first order metric perturbation. And the calculation of these introduces these type of source terms that extend right the way throughout the space-time. So the long established approach for obtaining solutions for each Fourier mode, whether at first or second order, is through the Green's function method of variation parameters, as shown here for a single scalar field. So you construct an appropriate basis homogeneous solutions and then integrate these against appropriate source terms to construct your inhomogeneous solution. So this has been quite instrumental in previous frequency domain calculations, but it does have some drawbacks. First of all, the boundary conditions for the are fairly straightforward to compute from Frobenius or asymptotic series expansions, but actually deriving them is quite tedious. Furthermore, these series expansions of the boundary conditions must be evaluated in the wave zone in order to converge at large radii. So now, for low frequency modes, which occur very large radius orbits and some modes of the eccentric orbit calculations, the wave zone moves into the very weak field, which means the integration of the homogeneous solutions accumulates a lot of error from the many steps in the numerical integrator that it has to take to extend this back down to the strong field. And lastly, the unbounded support sources, like we encounter at second order, are very challenging for numerical integration because these homogeneous solutions may not be regular. What we do is develop an alternative and more favorable geometric approach, building on the work of hyperboloidal methods in black hole spacetimes, and by avoiding the standard prescription of modeling our perturbations on Cauchy time slices, we choose an alternative hyperboloidal foliation with compactification. And then this is then implemented with a multi-domain spectral code for a scalar field toy model. So we capture with this model all the essential features we're going to see in gravitational self-force calculations while avoiding the niche technical issues like gauge choices. So we're just considering a particle with a scalar charge moving on a geodesic in a Schwarzschild background. So as I said before, the hyperboloidal coordinates foliate the future event horizon and future null infinity. And what this means is it allows us to include the black hole horizon and null infinity in our computational domain. So Here we follow the work in the so-called minimal gauge. So the transformation between the original Schwarzschild coordinates and the hyperboloidal coordinates reads like this. And what this means is this h, this height function, is given by the following expression in terms of sigma, and the along tau equals constant, so constant hyperboloidal time slices, scribe plus is now going to be at sigma equals 0, and the black hole horizon is going to be sigma equals 1. So this inverse is shown with this picture on the right here. So to make sure our transformed equations are in fact regular, we have to rescale our scalar field to take into the asymptotic fall off. And we do this by incorporating a conformal factor into our new scalar field like this. And the exponential factor you also see here naturally arises from the time transformation, but it means we actually factor out the oscillatory behavior you usually see with wave equations, which means you get more accurate and efficient solutions since you don't have to resolve the oscillations anymore. So our new hyperboloidal field satisfies a new equation with a new differential operator. This differential operator, as you can see from this alpha 2 appearing here, is actually degenerate at the boundaries. So it means at both boundaries, the principal part, the coefficient of the second order derivative term, will vanish, which means any regular solution to the differential equation will have the correct physical boundary conditions. Or put simply, the boundary conditions will follow directly from the differential equation, and you don't have to provide any data on the grid boundaries because there's no incoming characteristics to the numerical domain. So in the paper, we detail how to transform the scalar field equation for each type of source that I mentioned before, and discuss how to transform the equations for the flux and cell force. So this is quite useful when calculating fluxes towards null infinity, as you can now just read off the values for the radiated flux without the need for any extrapolation. So I should go through several results that demonstrate the effectiveness of cell force calculations using this method combined with the spectral methods that haven't gone into too much detail here in the interest of time. So this is a typical result. My slides aren't coming up. There we go. So what you see is the real parts of the hyperboloidal retarded field for the 1-1 mode particle of R equals 6, and for 60 Chebyshev nodes. And what you see in the insets here is the exponential decay of these Chebyshev coefficients from our spectral methods that indicate spectral convergence, which is what we want. And what you see in the right panel is the same fields as the left panel, but for a higher angular mode with a higher spectral resolution, so a higher number of Chebyshev coefficients. And you need these higher resolution at higher mode numbers because of the steep gradient you see that forms around the particle. And you see that even though you have spectral convergence, it's a slower spectral convergence. So to further validate our code, we can calculate energy fluxes and the local cell force. We go into more detail in our paper, but here I show you a plot of the L mode contribution to the regularized R component of the scalar cell force for the mode sum and effective source methods. So distributional source on the left and effective source on the right. And each line, what you see represents a subtraction of analytic regularization parameters designed to ensure the physical cell force is resolved from your divergent retarded field. So this is the blue line up here initially. And the key thing is to note here that one typically is only practically able to resolve to L is 50 modes, whereas our spectral hyperboloidal code can quickly and efficiently manage up to L equals 100 without too much difficulty for either method. And even though you have regularization parameters to speed things up, usually in some cases, like close to the light ring, you do need this large L mode spectrum. One of the most exciting things about our code, and the thing I will finish with, is that our code finds excellent agreement with regions of the parameter space traditionally not suited to perturbative computations, especially towards the weak field regime of large orbital radius that's usually covered by post-Newtonian theory. So to demonstrate this, and if it will appear in a second, there it is. What I'm showing here is a comparison with the T component of cell force calculated for flux balance laws with a scalar 4.5 Pn expression. And so the initial blue line is a comparison with the leading Pn term, and each subsequent line are residuals after subtracting successive Pn terms. So the plot on the left is a comparison of the T component of cell force normalized by the leading Pn term, and the plot on the right is a comparison of the parametric derivative of the same component. And this comes from the usual slow time terms that I was talking about earlier that appear in second order calculations. And what this shows is our numerical results are accurate even for extreme large radius orbits with RP up to like 10 to the 6m. So our hyperboloidal method, we hope, can be instrumental in future precision comparisons with PN theory for cell force problems with these unbounded sources, so like second order cell force calculations. So I will leave you with a summary of the points I've made and leave the rest of the time for questions. Thank you very much.
Okay, thanks very much, Benjamin. So one question which I had, you said in one of your last slides, your method got to L equals 100 compared to L equals 50. Do you have any kind of idea of what the implications for observation and for, I mean, observing these kind of events are from that improvement that you get?
So the improvement for L modes is less important than for improvement for large radius orbits, for example. But if you try and take a model like this and take it towards the light ring, what you see here is for a normal kind of radius orbit around 10m, and you see this nice mode behavior asymptotic for asymptotically large L. So out towards L equals 100. Now, what you don't get is when you go close to the light ring, you don't get this. It's very hard to see this same behavior, even with regularization parameters. So in order to find this for the large light ring, you really need to go out to high L modes to be able to get this nice subtraction that you see in the plots here. So that's the main advantage, being able to go into RGL. But it's also just a demonstration is that we can handle more extreme cases and more difficult sources than one would be normally able to. Does that answer your question, Daniel?
Yeah, I think so. Thanks. Okay, I don't see any other questions from the audience, but same as the last few times, if you do have any questions for Benjamin, please do ask them in the Slack channel, and I'm sure he can get to them later on.